So our next concept is configuration energy. This is the answer to the question of how much energy is there stored in some particular configuration of charges. So for example, suppose that I have some charge here, which will take to be Q1, and I have some charge here, which I'll take to be Q2, and I have some charge here, which I'll take to be Q3. What's the energy stored in this configuration of charge? That's the question we want to answer. I'm going to do it explicitly for this triangle of three charges. You'll see from the way that I do it that it's easy to generalize to any more complicated configuration of charges later. So the way that we're going to think about this is we're going to start by taking all three of these charges way off to infinity. So let me take this charge way off to infinity. Let me take this charge way off to infinity. And let me take this charge way off to infinity. Now, when I have three charges way off at infinity in three different directions, they're infinitely far from each other. The potential of this configuration of charges with everything infinitely far away is 0. So we're starting with 0 potential. And now let me start by bringing charge Q1 in from infinity to the place that I want to put it. So there's my Q1. And let's ask how much did the potential energy change? Well, I brought this charge from infinitely far away and I put it here, but it is still infinitely far away from charge 2, which is way off down there, and from charge 3, which is way off up there, or vice versa. All other charges infinitely far away, so the potential U was 0, and it's still 0. So far, nothing. OK. But now, let me drag charge 2 in from infinitely far away, and I'm going to bring it in and put it at the place where I wanted to have it, which was here. So I just brought charge 2 in from infinity down to there. And if these were both positive, then I had to do work, because charge Q1 and Q2 are repelling each other. I had to do work. That means that I'm adding to the potential energy. And so now I've just added some potential energy. How much potential energy have I added? Well, the potential energy that I've added is K Q1, Q2, divide by this distance right here, which I will call R12, the distance between charge 1 and charge 2 at their final locations. So it's KQ1, Q2 over R12. So that is the potential energy of this configuration of charges. But I'm not done yet. I wanted 3 charges. So now, with these 2 in place, I go get charge 3, and I bring it in from infinity, and I bring it to its spot, the place that I wanted to put it, which was somewhere right about here. And thinking of all of the charges as positive, as I brought this charge in, I had to do work because I was pushing this charge against the repulsion that it felt from the 2 charges Q1 and Q2 that were already in place. So I was doing work. That means the potential energy is increasing because I'm doing work that's increasing the potential energy. Bringing this charge in, placing it here, I'm doing work. Delta U is going up. Well, how much is it going up? So I have to do that integral of f dot ds, and now I use the superposition principle. As I'm bringing this charge Q3 in, when Q3 is there, the force that it feels, the electric force that it feels, is the vector superposition, the vector sum of the force from Q2 and the force from Q1. And I'm moving it in. I keep adding up all the f dot ds's, f dot ds's, f dot ds's. And the total that I get, that's what I want to write down here. And that's just going to be the sum of the contribution to the potential that is due to the force from Q2 and the contribution of the potential that's due to the force from Q1. So I just add up the 2 parts. And the reason that I'm allowed to do that is the principle of superposition, which was one of our basic facts, together with Coulomb's law, that we began 802 with. So when I do that, what will I get? Well, I'm going to get 2 terms, as I said. One of them is going to be K Q1 Q3 over R13. And the other one is going to be K Q2 2q3 over r23. And what are r13 and r23? r13 is this distance, and r23 is this distance. So this is my final answer. And if you look at the final answer, there are 3 terms in it. And you can see that this one we could call U12. This is the potential energy associated with charges 1 and 2. This one we could call U13. This is the potential energy associated with charges 1 and 3. And the third contribution to the configuration energy, the total potential energy of this configuration, is U23. And this is the potential energy due to the interaction between charges 2 and 3. And you add them all up. Now, it may be bothering you that it seemed like it was special that I started with charge 1. But if you think about it, you'll realize that if I had started with charge 2 or 3, I would have gotten the same final answer. So I could tell the same story all over again, but I start by bringing charge 3 in. That costs nothing. Then I'll bring charge 2 in. That'll give me a term U23. And so the first term I would have written down would have been this term. And then I would have said, oh, I'm bringing charge Q1 in. It's feeling a force from both 2 and 3. I use superposition. I vector add the forces. I get 2 terms in U. And those 2 terms would have been this term and this term. And so I would have ended up with the same final answer. So it does not matter which charge I bring in first, which charge I bring in second, which charge I bring in third. The potential energy of the configuration that I calculate will be the same, will be given by this result.